Thank you, Molly. Hi, everybody, and thank you for joining us today. I am Shelly, and I'm here with my colleagues Artemio and Gage. Medical image interpretation and diagnosis are critical to driving quality healthcare and tedious. Pathologists could be spending hours evaluating tissue images and making observations. AI can analyze this existing data and help with the diagnosis. One of the key barriers that AI in healthcare in general is facing is explainability. So today we are going to demonstrate an AI product prototype, which helps diagnose memory carcinoma, which is presence of tumors in breast tissue, and also provides some explainability features. It's a four-stage solution where the input is a whole slide image. It first tries to find out the areas where it detects mitotic figures. It then takes those figures and actually classifies them as mitotic or non-mitotic. The last two stages of the product are related to explainability features. I'm going to hand over to Gage, who will take you through the next steps.
Thank you, Shelly. Hi, everyone. My name is Gage, and the most important step in our project was really understanding our data. So we're working with whole slide images, which are very high resolution light microscopy images. And in this case, we're working with whole slide images of canine breast cancer tissue. So in this data set that we based our work on, the authors had gone through 21 of these whole slide images and labeled cells throughout the image as either mitotic. So here's an example on the right of a mitotic figure, which basically means a cell under a state of cell division, and non-mitotic figures. So in total, the authors had annotated about 36,000 non-mitotic figures and 14,000 mitotic figures in this data set. So in order to use this data, we needed to break it down into smaller pieces to build our models. So on the left here, we generated a 512 pixel image data set for our object detection model. So here, these are 512 by 512 images with bounding box info around the annotations. On the right here, we generated 250 pixel patches for a patch classification model, which then further subclasses the data into mitotic figures. Here's an example on the left, and non-mitotic figures on the right. So for the real world application, we want to be able to take in this whole slide image, which is a very large image, and break it down into smaller pieces in order to get it into the right input size for the object detection model. So in the data handling portion on the left, we'll take an unseen whole slide image and systematically segment that image into overlapping 512 pixel patches, which are then fed to our object detection model. So then the object detection model is effectively scanning the entire whole slide image to generate candidates for mitotic figures. And so it generates 250 pixel patch candidates, which are then fed to our cell patch classification model. So this additional step sort of acts like a double check to the object detection model and adds a level of robustness to the predictive AI portion here. In addition to that, the cell patch classification model also generates image embeddings, which then we can feed forward to our explainable AI portion here on the right. And that includes visual explainability through GradCam and class activation maps, and a textual explainability through a dual encoder model. So diving into the modeling, for our object detection model, again, we're working with 512 pixel data here with bounding boxes to train our model. And we trained or fine-tuned a faster RCNN object detection model in PyTorch and achieved a mean intersection over union of 0.86 and mean scores of 0.88. And in the table at the bottom here, you can see how we broke down our training and validation and test sets. Moving on to our cell patch classification model. Again, we're working with 250 pixel patch data here, broken down into mitotic and non-mitotic figure examples. And we fine-tuned a ResNet 18 network in PyTorch and achieved an accuracy of 0.87 and an F1 score relative to mitosis of 0.76. And again, here is the breakdown of our training, validation, and test sets. And with that, I'll hand it over to Shelly to go over the visual explainability with GradCam.
Thanks, Gage. For visual explainability, we have used GradCam, which is gradient weighted class activation map. We did it at the class cell patch classifier model. So it takes at the last convolution layer, which feds into the fully connected layer, it takes all the gradients with respect to the task, which is classification, and combines them and processes it through a ReLU function. It results in a very localized coarse image, as you see in the middle, and it brings out all the salient regions of the input image, which have led to the classification of a targeted class, which is for us was mitotic. So when the input image is superimposed with the heat map, we get this output, which is a very creative and great visual explainable, highlighting the portions of the input image, which led to the classification. And Artemio will explain the last stage of our model.
Awesome, thanks, Shelly. So we've built a dual encoder that allows us to take our images, the 250 pixel training data, and automatically determine what text is being described on the image. And here we're using artificially generated text, so there are no evaluation metrics here. We wanted to build a prototype that can demonstrate that we can take an image and automatically output text. And you can see from left to right, we're taking separate image and text embeddings and combining them through the dual encoder with a joint embedding representation. So in our demo, you'd see that once an image is inputted, a textual output is due to because we're allowed to combine similarities between our embeddings. And with that, I'm going to pass it over to Gage to go over the demo. Oh, sorry, we're going to go through the deployment stack. My apologies. So on the left side here, you can see that from top to bottom, we're using data science based off the SQLite data that we've pulled on these images and inputting them into Python. We built our entire application in Python with PyTorch, TensorFlow, and FastAPI, and we've containerized everything. And as you can see in the deployment stack, we've containerized everything in Docker and implemented that in AWS EC2, which is then rendered in the web application. On the right, you can see that we've broken down the stages of our application and the technologies that we've used, and we want to show the runtime. For a given whole slide image, we estimated about 2 to 3 minutes per whole slide image. Now I will pass it over to Gage for our demo.
Thanks, Artemio. No worries there. Alrighty, so this is our web application, and we'll share the URL to our web app here after the presentation. So in the product highlights tab, we can kind of see the general overview of the modeling that we used, brief descriptions of each stage in our ML pipeline. And in the team profile has a little background on the team. And the inference tab is where all the magic happens. So this is where the user, presumably a pathologist, can go in and upload an image of a whole site image that they want to analyze. So they'll be able to click here and upload an image that they want to analyze. So in this case, a whole site image. Now I've already run some of these for time's sake, but to show you an example of what a whole site image looks like, this is a 7,000 by 5,000 pixel section of a WSI. Keeping in mind, WSIs are very large files on the order of 2 gigabytes, and this is a smaller subsection that we want to analyze. So after we've uploaded and processed the image, you can see the uploaded image here on the left and the heat map image on the right. So the heat map image has the GradCam class activation maps overlaid over the input image. And these correspond to mitotic detections that were made. Moving on to the table in the middle here, this is the predicted image class. So 0 for mitotic and 1 for non-mitotic, and the associated text explanation. So the idea here is that the pathologist, when they're going through and analyzing this image, they can go through and read through these text explanations that were generated to help them analyze the WSI and help eventually diagnose the cell tissue sample that they got the WSI from. And lastly, scrolling to the bottom here, this table has the total number of predictions and the number of mitotic detections that were made. So on this particular whole slide image, about 22% of the detections were mitotic figures. Here I have another example of a whole slide image. So same deal, upload image, heat map image with text explanations. And lastly, to test the robustness of our models, I have uploaded a picture of my cat here. And although the object detection model did make some detections on the input image, fortunately, none of them were mitotic figures. So I can conclude with a reasonable degree of confidence that my cat is cancer-free. So we'll turn it back over to Artemio here to go over the last portion of our presentation.
Awesome, thanks, Gage. So AI with medical and business value. We've developed a tool here that will give immense amount of value to pathologists in the healthcare sector. Here, we've increased the whole slide image throughput. We've enforced transparency with automated explanations, and we have efficient implementation. You can imagine that we've reduced the amount of time it takes for pathologists to count mitotic cells, and we've turned that into a 2 to 3 minute upload from an image and runtime. And so this is the amount of value that we give no matter what pathologist is using it, whether they're in the private sector, they're in the hospital setting, or in the community. And into the next slide, the future of AI in pathology is bright. In terms of the future work, where do we go from here? We'd love to extend our models and our data to human data. Our training data is composed of canine breast cancer tissue, and so we want to be able to generalize that using human data. As you've seen from our demo, we'd like to make some UI enhancements, make it more readable, clickable in some areas where there is mitotic regions. And we would finally like to apply real-world text data. We built a prototype using fake data, but you can imagine the amount of clinical data that's out there where we can match up text data to clinical data from images. And with that, I'd like to thank everyone for listening to our presentation, and I'd like to open up the floor to the audience for questions.